In this bonus video, we're going to find the general solution to a linear differential equation with an inhomogeneous term on the right-hand side. And this one's going to be a little bit more complicated than some of the other examples I've done. All right, our plan for finding the solution is to first find the complementary function, which I'm going to denote y sub c. That's the solution to the homogeneous problem. Then we'll find a particular solution, which I'll denote y sub p. And our general solution to the original problem is going to be the sum of the solutions that we find in steps 1 and 2. But before we do that, I'm going to rewrite this differential equation using operators. If I use operators, and by operators, I mean that I'm going to use capital D to denote derivatives. So I have d squared plus 4 applied to y, and that's equal to cosine 2x. Okay, I'm doing that because I will use this, the form of this operator throughout the problem. So let's do the first thing in our plan here. We're going to find the complementary function, y sub c. And y sub c is the function that satisfies yc double prime plus 4yc equals 0. So it satisfies the associated homogeneous problem where we pretend that our right-hand side is 0. We can use an auxiliary polynomial to solve this. P of r in this case is going to be r squared plus 4. And if you're wondering where that's coming from, let's look at our operator notation. The auxiliary polynomial is associated with this operator, where instead of a capital D, we use r. This tells us that the roots of this polynomial are plus or minus 2i. And so from there, we can immediately write down y sub c is going to be, we normally would have e to the something x here, but our complex roots have 0 real part. So this would be like e to the 0. So we don't need to write that term. It's really just 1. And left over, we have cosine c1 cosine 2x plus c2 sine 2x. Okay, we're just going to remember that we have this and kind of push pause as we go on to step 2 of our plan, which is finding a particular solution. Okay, we're going to do this using annihilators. And the annihilator of our right-hand side here, in this case, capital F of x is cosine 2x. That's our right-hand side. The annihilator of this function is a of d equals d squared plus 4. So remember, we look at our right-hand side and we ask ourselves, what polynomial differential operator would have given me a term like this in a solution to a homogeneous differential equation? So that would mean that I would have had to have a root that was plus or minus 2i. And so the polynomial I'm looking for is d squared plus 4. Okay, so then we apply a of d to the original ODE. I'm going to apply it to both sides of this function. On the left, we would get d squared plus 4, d squared plus 4, all applied to y. And on the right, we would get 0. Because if I apply the annihilator, a of d, to this right-hand side, I'll get 0. That's exactly how we chose this function, this operator. And let me point out that this first one, or this operator here that's closest to y, that's coming from our original equation, right? That's this piece. And the operator I'm applying here is my annihilator. So original equation here, annihilator is there. Really, now I could rewrite this as d squared plus 4 squared applied to y, because really I have 2 copies of the same operator. Well, that tells me that the solution to this new homogeneous equation is going to come from writing down the polynomial r squared plus 4 squared and finding the roots of this auxiliary polynomial, which has roots of plus or minus 2i, but this time each of those roots has multiplicity 2. By that I mean they're repeated twice because I have this squared here. So multiplicity 2. Okay. Now, if I were then to write down the general solution to this new homogeneous problem, I would write down that y is equal to c1 cosine 2x plus c2 sine 2x. Again, I'm using the roots of this polynomial here. And I had multiplicity 2, so I now have to add these terms, c3x cosine 2x plus c4x sine 2x. All right. Now from here, we're doing all of this work to figure out what form our particular solution should have. And the form that it's going to have is anything in this function that does not already show up in my complementary function. So let's look at our function we got here. These first two terms show up in y sub c, so we're not going to use those. These last two terms do not show up in y sub c, so these terms will be in our trial solution. All right, so I'm going to go on to the next page here. All right, I just have a summary of what we have so far up here. We're finding the general solution to this equation. We have our complementary function, and we still have our general plan overall. Now that we have a trial solution, we're going to substitute the trial solution into the original ODE. I'm going to move this up a little bit because I don't want to run out of room. Our trial solution that we just found, I'll rewrite it here, looks like, so the trial solution tells us that the form of our particular solution is going to be some constant a times x cosine 2x plus some constant b times x sine 2x. Really quickly, I know that back here I had C3 and C4. Again, those are just constants, but I don't want to keep writing subscripts. So in my trial solution, I'm just calling C3 capital A and C4 capital B. If you like, you can leave them as C3 and C4, that's fine. Okay. Well, I want to substitute this function into the original ODE. Well, that means I'm going to need two derivatives because I'm going to need to plug that in there. So let's compute some derivatives before we plug things in. So y sub p prime, I'm going to have to use product rule twice here. I'm going to end up with a cosine 2x minus 2a sine 2x plus b sine 2x plus 2bx cosine 2x. Oh, I'm sorry, I'm missing an x here. I was missing an x there, in case you missed that. Okay, that's the first derivative. And now I need to take another derivative. So I'm going to do some more product rules. So I'll end up with negative 2a sine 2x minus 2a sine 2x minus 4ax cosine 2x plus 2b cosine 2x plus 2b cosine 2x minus 4bx sine 2x. So this derivative is coming from this term. These two terms here are coming from the derivative of this term. This term here, 2b cosine 2x, is coming from the derivative of this term. And these last two terms are coming from the derivative of the last term here. All right, I'm ready to, well, actually, let me simplify this first, and then I'll plug everything in. I'm going to combine these two terms and these two terms just to make my life a little easier. I'll have negative 4a sine 2x, and then this term remains the same. And then plus 4b sine 2x, and then this last term remains the same. Okay, now I'm ready to substitute everything in. So this whole thing is y double prime. That's what I'm going to write down first. And then I want to add 4 times y. So that tells me I'm going to write down y double prime, negative 4a sine 2x minus 4ax cosine 2x plus 4b cosine 2x minus 4bx sine 2x. Okay, plus 4 times y, which is ax cosine 2x plus bx sine 2x. All of that is equal to cosine 2x. So just to make it super clear, this whole thing is y double prime, where the y that I'm plugging in is my trial solution. And this other term here, this other term here is plus 4 times y, and then I'm setting all that equal to my right-hand side. All right, well, let's combine like terms on the left-hand side here. We'll end up with 4a sine 2x stays the same, but it looks like negative 4ax cosine 2x is going to cancel with 4ax cosine 2x over here. Same thing with this negative 4bx sine 2x. I've got plus 4 times bx sine 2x. So those terms are going to disappear. I'll end up with negative 4a sine 2x plus 4b cosine 2x. And that's all equal to my right-hand side, cosine 2x. And now I want to equate the coefficients on sine on the left-hand side with the coefficients on sine on the right-hand side. And then I want to equate the coefficients on cosine on the left to the coefficients of cosine on the right. Well, I don't actually have any terms with sine on the right. So if you like, if it helps you remember what you're doing, you could write plus 0 times sine 2x. So the first equation I'm going to write down is that negative 4a should be equal to 0. And that's coming from my terms on sine on the left and right, those coefficients. So that tells me right away, actually, that a is 0. The next equation I'm going to write down is that negative 4b, positive 4b. There we go. 4b should be equal to 1. That's from me equating the coefficients on cosine on the left and right, where over here I just have a 1 times cosine. That tells me that b is equal to 1/4. Let me move a few things up a little bit because I want to write everything on the same slide here. All right, so what did we just do? We had a trial solution that we figured out should be this form, and we plugged it in to try to figure out what a and b should be. We found out that a is 0 and b is 1/4, so I'm going to write down our particular solution. Particular solution is going to be 0 times x cosine 2x plus 1/4 times x sine 2x. So really it's just 1/4 x sine 2x. And last but not least, where we've finally reached our third step of our plan. We found the complementary function, we found a particular solution, and our general solution is just the sum of those two things. So the general solution is y of x equals c1 cosine 2x plus c2 sine 2x plus 1/4 x sine 2x. And I will go ahead and put a nice box around our solution. All right, that's the end of this problem. Let me know if you have any questions.